Yeah, good afternoon. Once again, I am here with next lecture on convergent sequences. Now we start with the theorem on limits. This is very important theorem and it is referred in your syllabus also. The theorem is let an and bn be sequences of real numbers and k is any real number. We suppose that the sequence an converges to a and sequence bn converges to point b. Then we have to prove that sequence created by adding these two sequences an plus bn and the sequence k of an and sequence a and bn means multiplication of two sequences. These all are convergent sequences and they are converging. If we add the sequences, they are converging to the addition of their respective limit points. And similarly, if I multiply the sequence by common number scalar, say k, then its limit is also k times a. And in case of multiplication, their limits are also multiplied. And then d part, here this is a case of division a upon b. Since it is in denominator, the limit of bn is b, it should not be equal to 0 and the elements should be non-zero. Then this converges to the point a upon b. Then the proof of these results, we start with first result. We have two sequences a and bn. By definition, for every epsilon, since an converges to a, there exists some natural number n1 such that an minus a less than epsilon by 2 for all n. This is by definition, right? Again, similarly, bn also converges to b. So again, by definition, there exists n2 belonging to some natural number such that mod of bn minus b less than epsilon by 2 for all n greater than equal to n2. Now again, as we did in earlier lectures, I want to combine these two. I take the maximum so that those both the equations holds together, right? Then I take maximum value. Then for this n greater than equal to this n maximum, I combine an plus bn minus a plus b can be written as, I write it as an minus a plus bn minus b. Apply triangle law. This is less than equal to mod of an plus bn, and from these above equation, this is less than epsilon by 2 plus epsilon by, it is epsilon. That's why we have taken a epsilon. Why? Because I want here epsilon. So we have proved by definition the an plus bn has a limit point a plus b. Similarly, part b, here we have taken k. If k is 0, there is nothing to prove. Suppose k not equal to 0. Since n is convergent, I take epsilon as epsilon upon mod of k. Why? Because I have to counter this in next equation. Epsilon is any positive number. So epsilon is positive number, mod of k is also positive number. This is valid. Now I have to prove for this equation k times an minus k times a is written as, k is taken as common, this an minus a. But because of this equation, this an minus a is less than epsilon upon mod of k. Why I have taken here mod k? Because I know that here I am getting mod k, this is positive number. That's why I have taken. This is the liberty we have because convergent sequence, in case of these sequences, we can take any positive number. Epsilon is any positive number. So I have taken epsilon by to counter so that this k and k cancel out and I thus get the value. So this is less than epsilon. Why? Because this is less than this, k and k cancel out. So k and minus this means limit point of this k and is k a. Next is multiplication. We have studied in previous lectures every convergent sequence is bounded sequence. So we will use that concept here. Since n is convergent, it is bounded. So now I write a and bn minus a minus b as an minus, I take one sequence, the limit point of the sequence, and then minus ab, and when I solve it, I mod of n, this is convergent, this is less than mod of m, and this is it is convergent for n belonging to n. We have an minus a less than epsilon upon mod b. This is our, because this is positive value, right?